Hello everyone, my name is Nick Vitagliano and I am a junior mechanical engineering student at Penn State University. I'm here to talk to you about the current state of the fused deposition modeling, or FDM, 3D printing process at Microplastic Solutions. The company's current process prints regular, non-reinforced polymers in their customized additively manufactured parts and components. However, advancements in manufacturing technology have improved upon regular polymer 3D printing by introducing fiber-reinforced polymers. Today, we're going to talk about potentially upgrading the company's current standard FDM 3D printing process to enable the printing of reinforced fibers. Specifically, we'll take a look at why reinforced polymers are useful in the first place, the differences between printing regular and reinforced polymers via FDM, and whether or not it is feasible and logical to implement this advanced manufacturing process. So let's begin with why reinforced polymers are beneficial in manufactured products. Several studies have shown that when compared side by side with regular polymers, reinforced polymers exhibit superior mechanical properties and higher overall performance. Particular properties of interest include ultimate tensile strength, fracture strength, and elasticity or stiffness. These property values increase because of the support the reinforcing material provides. When a load is applied to these parts, the reinforcing fibers absorb much of the stress applied, supporting and effectively protecting the weaker plastic material it is enclosed in. For example, when weight is added to the fiberglass reinforced onyx material in the far left of this video, the bracket is able to support it with little deformation. The direct comparison to this is the bracket to its immediate right, the non-reinforced onyx polymer. Although this bracket does not critically fail, there is a significant amount of added deformation in the bracket. This holds true for all direct comparisons of regular versus reinforced polymers. The reinforced polymer always outperforms the regular polymer. The fibers found in reinforced polymers are not necessarily special materials. Fiberglass is one of the most common materials used for reinforcing polymers. It is sturdy and cost-effective and can multiply the strength of regular ABS or PLA by several times. Carbon fibers are also used for polymer reinforcement. This material is extremely stiff and can behave like, or sometimes above, 6061 aluminum. Finally, Kevlar can be used to greatly increase the toughness and shock resistance of 3D printed parts. The application of the part determines which material will be used for reinforcement. Now that we understand why reinforced polymers are beneficial to manufactured products, we'll discuss the differences between the FDM printing processes for regular and reinforced polymers. Although the FDM process at microplastics is large scale, it can still be modeled and explained via a simple desktop 3D printer. Regular polymers like ABS and PLA are sold in spools. These spools of filament are fed into the printer extruder, and a set of gears or cogs helps keep the filament moving, as well as set the feed rate. After the filament is passed through the feeding stage, it is sent into a heater which liquefies the material and makes it easy to be extruded. Once the polymer is soft enough, it is pushed through the extruding nozzle and begins to be deposited layer by layer on top of the print bed. On most 3D printers, the print bed is fixed and the nozzle is connected to a multi-axis directional system, which allows the material to be deposited in user-specified locations. Conveniently, printing reinforced polymers is not difficult to do, but the base FDM process must be modified slightly. There are two main methods to print reinforced polymers through FDM 3D printing. These methods are the chopped fiber method and the continuous fiber method. The chopped fiber method works exactly how it sounds. Bulk amounts of reinforcing fiber material are cut up into tiny strands. These fiber particles are then mixed into a vat of liquid polymer resin, the result then being a suspension of the two materials. Once the mixture is cooled and hardened, it is extruded into long, drawn-out cylindrical filaments and can be placed on spools for sale or sent directly into the FDM printer. Surface finish, however, could be negatively impacted depending on how finely cut the chopped fibers are. The continuous fiber method has two variants to it. The first variant requires a printer head that has two feed inputs, one for the polymer filament and one for the introduction of continuous strands of fiber. When the polymer is heated inside of the print head, it surrounds the fiber and encloses it in a shell. The output from the nozzle is then a strand of fiber encased in the resin polymer, which hardens on the build tray. The second variant of the continuous fiber method requires a vat of liquid resin. The continuous strand of reinforcing fiber is sent through a series of rollers, which submerges it in the vat, once again encasing it in the polymer. The fiber is then drawn out of the vat and through the nozzle, where it is then deposited on the build tray. Both variants produce the same result. Each layer of material deposited on the build tray consists of a long continuous strand of reinforcing fiber encased in the resin polymer being used. These layers are then stacked on top of each other, one by one, until the product is complete. The following video shows an accelerated time-lapse of the material layers building upon one another via FDM. Now that we understand how both processes function, we will determine if implementing the advanced printing process is worthwhile based off of its explicit advantages and disadvantages. As touched upon earlier, reinforced polymers certainly have their advantages when compared to non-reinforced polymers. Their greatest advantage comes in the form of their increased mechanical properties, including strength, stiffness, toughness, and others as we've seen before. Reinforced polymers also open up the potential for a wider line of products. Microplastics could add a line of identical reinforced parts to their current non-reinforced product line and offer pricing differences between the two. This provides the customer with more options and lets them select the most suitable product for a specific application. When compared to non-reinforced polymers, the production time essentially remains unchanged. As we've seen, the introduction of the reinforcing fibers via the chopped fiber or continuous fiber method is rather seamless. Solidification time remains unchanged because the fibers are not being melted. The only liquid component is the resin polymer. So production time will virtually stay the same as long as the polymer being used is the same. Finally, it can be relatively simple to implement this process into an already established FDM system by using the chopped fiber method. All that needs to be done here is to change the type of resin purchased from the supplier from regular to reinforced chopped fiber resin. As with any process, printing reinforced polymers also has its fair share of disadvantages. The largest is the potential increase in defect propagation. Chopped fiber resin has the tendency to have voids inside of the filaments, as the fibers can displace the liquid resin during mixing. Uneven material distribution can lead to anisotropic conditions and create uneven stress regions when the part is completed. If using the continuous fiber method, it is possible for the polymer shell surrounding the fiber to be uneven, resulting in slightly different layer thicknesses and summing up to create a deformed part. There are methods to prevent or catch these defects, such as a layer ironing process, which flattens out each printed layer, or by performing manual inspection. However, these techniques can create additional costs and complexity to the process. Since the current FDM process is not entirely capable of handling these reinforced fibers, an added tooling cost must be considered to replace the current technology, whether it be in the form of added machinery or possibly an entirely new printing system. Additionally, variable costs will increase as reinforced polymers will require both the fiber and resin as inputs instead of only the plain resin. Finally, reinforced polymers limit the geometric design complexity of the part. This can really be visualized if using the continuous fiber method. A solid continuous fiber cannot be oriented and placed as freely as a purely liquefied resin can be. It can be possible that reinforced polymers might limit the breadth of design solutions that microplastics provides to its customers. Now that we have seen the pros and cons of the process, a manufacturing readiness level assessment, or MRL, will be performed. MRLs consider a wide variety of factors to determine how suitable a manufacturing process is to be implemented. Some of these factors include the materials and tooling required, the maturity of the technology and the process, potential risks and risk likelihood, past industry success with the process, and an overall cost-benefit analysis. After analyzing all aspects of the process, I believe that the printing of reinforced polymers via FDM receives an MRL score of 8 for a few reasons. The process is already well defined and has been used in industry before. Also, reinforced polymers could possibly expand the company's product line, and they may exhibit success that other companies have in the past. However, as with any AM process, it is a fairly new technique, and without having enough customer need, the financial and production risks posed can be high. Despite the process seeming more than capable, I would not recommend implementing it until the demand from current customers for reinforced polymers is high, or if its implementation can attract enough new customers to justify the costs. Today, we discuss the potential implementation of reinforced polymer 3D printing via FDM at Microplastic Solutions. Despite the promise that the technology may hold, I recommend its use to be avoided until enough customer need arises. Thank you. These are the sources of information for this project. As most of these websites sold both regular and reinforced polymers, they appeared to be free of bias and covered both advantages and disadvantages of each process.